Yeah, sure.
All right, well, thanks everyone for coming to Stanford Bitcoin Club last event of the year. We're very happy to welcome Elaine, who is an associate professor at Cornell and a co-founder of IC3 and Thunder Token. She co-authored the first peer-reviewed publication on Bitcoin and the first one on decentralized smart contracts. She was also one of the first to teach smart contract programming. She has won numerous awards, including a Packard Fellowship, a Sloan Fellowship, and ONR YIP Award, and various Best Paper Awards. She obtained her PhD from Carnegie Mellon University, and prior to joining Cornell, she worked as an assistant professor at UMD. And today she'll talk about some.
Okay, yeah, thank you so much for the introduction. I'm very happy to be here. Today I'm going to be talking about Thunder Token, a fast and high throughput cryptocurrency. You can think of it as a very fast version of Ethereum. We are going to support Ethereum smart contracts. Okay, so 2017 is said to be the year of the ICOs, and 2018 is the year of the dApps, right? So I'm sure most of you have heard of dApps. These are applications built on top of decentralized blockchains. Now there are many exciting dApps, right? There's sharing economy, like putting Uber and Airbnb on blockchains. There are games, of course, like Cryptokitties. There are lots of others, like decentralized exchanges, prediction markets, and so on and so forth. Well, despite all of this excitement, there is a truth that everyone knows, but no one particularly likes admitting. Basically, today's blockchains are too slow for all these dApps. With today's blockchain infrastructure, none of these dApps will actually take off at scale. And let me give you an example. This shows Ethereum transaction fees over time. And as you may well know, a particularly exciting time for our cryptocurrency community is in December last year. And this was when Cryptokitties came about. Right? So Cryptokitties is this collectible game. You can breed kitties, and some of the rare breeds can sell for like 100K USD on Ethereum. And now this is, of course, it's a very exciting game, but in comparison with social network games, mobile games, and all these traditional games, it's not like they have a huge volume. Nonetheless, the single game alone was sufficient to overload Ethereum entirely back in December. And back in December, Ethereum was 90% utilized, and the transaction fees were like 1 million per day. Okay, so this is how bad it got. And therefore, I believe that the most exciting and most challenging problem our community faces today is scalability. And this is the problem that we have to solve. In our company, Thunder Token, we believe that we have the best technology out there to overcome this challenge. Even with a single shard, we can achieve 100x more throughput than today's blockchain. And we can achieve transaction confirmation in less than a second. Okay, so in today's talk, I'm going to tell you about the core consensus protocol that enables such a fast cryptocurrency. It's called Thunderella, and this is joint work with Rafael Pass. So of course, it takes more than just the consensus protocol to build a cryptocurrency, right? You have to have the right incentive mechanisms. You have to have the right governance policy. In the interest of time, today I'm only going to focus on the consensus protocol. And if distributed consensus is new to you, don't worry. And this is also meant to be somewhat of a crash course on distributed consensus. And if you have any questions, by the way, you should feel free to interrupt in the middle of the talk. Okay, so to understand consensus, I have to first define the problem I'm trying to solve, right? So we know that we want to build a public ledger. So let's actually imagine a traditional scenario with Google Wallet servers. So these set of servers, they want to agree on an ever-growing linearly ordered log of transactions. Okay, and state machine application is also often called linearly ordered log or consensus. And for the rest of the talk, all of these terms pretty much mean the same thing. So now there are two important security goals that we have in mind, namely consistency and liveness. So consistency says that all of the honest nodes must agree on the log. Okay, so the network may have delay, right? So it could be that, let's say, Bar's lock progresses a little faster than mine. That's okay. But at the end of the day, nonetheless, all the nodes have to agree on the lock. Now, what does Liveness mean? Liveness says that whenever an honest client submits a transaction to the system, very quickly, all of the honest nodes logs must contain that transaction because we don't want to wait forever for our coffee. Okay, so now you may ask, this seems like a very boring problem. What is so difficult about building a distributed linearly ordered lock? Why is this even an exciting problem? Indeed, if all of these nodes are honest and they correctly follow the protocol, this would be a trivial problem. But what makes it challenging is when some of these nodes can be compromised. Like let's say they have malware and the attacker can exploit the malware. And now these compromised nodes can deviate arbitrarily from the protocol. And we want to say that even under this scenario, the remaining set of honest nodes must nonetheless satisfy these important security properties. Okay, so that's why the problem is very exciting. In the real world, like these nodes, they can have like incentive to misbehave. For instance, they want to double spend their coin, and that's also another reason why they may not correctly follow the protocol. Okay. Well, as it turns out, state machine replication is not a new problem. It's actually a 30-year-old problem that the distributed systems community has studied a lot. And in Silicon Valley, almost every company actually deploys state machine replication protocols for replicating their computing infrastructure. Right? So Apache Zookeeper is an open source implementation of what's called Paxos. Paxos is like a crash fault tolerant version of a state machine application. So all of these companies, for instance, deploy Apache Zookeeper. Now, traditionally, when we talk about consensus, the kind of scenario that we have in mind is exactly what I talked about, right? There's a single organization like Google or Facebook. We have like, let's say, a dozen nodes, and these nodes are interconnected with fast local area network. Okay, so consensus itself is not new. What is new here is the large scale, right? With cryptocurrencies, we are looking at internet scale deployments. We are looking at thousands to millions of nodes. And as it turns out, consensus on a large scale is very much a different beast. It is a much more challenging problem than the classical setting. And this perhaps explains why all these ICOs, all these cryptocurrency companies, everyone's rushing to create, invent, and implement their own consensus protocol. So at the end of the day, when you think about it, this doesn't make any sense at all, because consensus is just as tricky to implement, to design, as crypto protocols. And as we all know, if you have taken like an undergrad security class, the first thing the instructor may tell you is don't roll your own crypto. And the same here, right? You shouldn't be rolling your own consensus protocol. Okay. So, here are the two questions that I want to try to answer in the rest of the talk. Number one, like I said, why after 30 years of research and development in this area, there still isn't a dream large-scale consensus protocol? Why is it that everyone's inventing their own protocol? Okay, and number two, I'm going to tell you about what I believe to be the dream large-scale consensus protocol. Okay, so we'll start with number one. Any questions at this point? Okay, so to understand why there still isn't a dream large-scale consensus, it helps to look at the consensus landscape. Okay, roughly speaking, there are two broad classes of approaches towards consensus, and I'm going to call them classical and blockchains. So classical protocols are like those protocols that Google and Facebook deploy, right? So representative protocols are like PBFT and Paxos. And what do we know about classical consensus? We know that, let's say when bandwidth is abundant, right? Like in Google, Facebook is fast local area network. These protocols are fast most of the time because you can confirm transactions in constant number of network round trips. Okay, but these protocols are notorious for being extremely complex. And the complexity makes it very difficult to implement, to maintain, and to deploy on a large scale. And also these classical protocols, they don't actually scale very well to a large number of nodes. Now, of course, the more exciting approach is we have all this hype here is the blockchains, right? And then the first blockchain style consensus protocol is Nakamoto consensus, and that is the protocol that underlies Bitcoin. Okay, and what do we know about blockchains? So first, I want to tell you that blockchains, they're not just an empirical success, they're actually a mathematical breakthrough. Because now actually, the academic community have like looked into the mathematics behind these blockchain style consensus protocols. And we understand that the mathematics behind these protocols depart completely from classical. So this is quite amazing. It's a theoretical breakthrough. So now blockchain protocols have two compelling advantages. One is that they're extremely simple, right? These protocols, the rule is that everyone looks for the longest chain and they try to extend the longest chain by mining the next block. And that's it. Extremely simple to implement. And these protocols are very robust on a large scale. And this has been empirically proven, right? Bitcoin has been up and running for the past 10, 11 years already. Okay. Now, the main drawback with blockchains is that they're incredibly slow, right? So for Bitcoin, as we all know, every block is 10 minutes. And if you want to have enough confidence, you have to wait for like 6 blocks. And that's, easily an hour. Like, do I have to wait for an hour for my coffee? All right. So you may ask if like the slowness is inherent. And the answer is actually yes, the slowness is inherent because, so as I said, we now mathematically understand these protocols. And the block interval actually has to be 60 times larger than the maximum narrow delay to tolerate 49% attack. So that's why some of the slowness is inherent. And okay, so finally, another thing you may be concerned about is the energy waste. Like Nakamoto consensus has to solve computational puzzles, and the energy spent on mining Bitcoin is right now, I think it's higher than the total electricity consumption of Iceland, which is pretty amazing. And this is only to confirm 7 transactions per second. Okay, all right. For the purpose of this talk, I want you to take a leap of faith and believe that this energy waste problem has already been solved. So we had an earlier work which shows how to remove the proof of work and still be able to emulate the mathematics behind Bitcoin. So for instance, we can build these protocols based on top of proof of stake assumptions. And now for the rest of the talk, whenever I mention blockchains, I mean both proof of work and proof of stake style approaches. If in particular, if you are worried about energy waste, you should think of it as a proof of stake blockchain. And this will not be a focus of this talk. Okay, so now even if we can solve the proof of work problem, we still haven't solved the slowness problem yet. Okay, so therefore we are still missing the dream large-scale consensus protocol. And now I'm going to tell you what I believe to be the dream large-scale consensus protocol. Are you ready? Okay, good. So here's the plan. I'm going to start by explaining classical approach to consensus. And in the middle, I'm going to get stuck. And when I get stuck, I will show how to combine the best of both worlds to get the dream protocol. Okay, so we'll start with classical consensus. And here is the scenario that we are working with today. The guy in the middle is Vitalik, and everyone knows him. He's the founder of Ethereum. We have a committee of voters, and today the committee of voters are superheroes. Okay, now some of these voters can be corrupt. Like in this case, Loki is corrupt, and he may not follow the protocol honestly. And the leader can also be corrupt, by the way. Okay, so of course, I didn't tell you how to select the committee, but for now, I want you to believe that there is a mechanism to select the committee. For instance, on the decentralized cryptocurrency, you can select it from a stake distribution. Okay. So I'm going to tell you an extremely simple voting-based protocol, and I want us to think together what properties this protocol can achieve. Okay, so let's begin. Here's the protocol. Step number 1, the leader is going to make a proposal. And the proposal contains a sequence number and a batch of transactions. So in practice, you always want to confirm a batch at a time. But in the talk, I'm going to call this a single transaction just for simplicity. Okay, so the sequence number is going to define where in this linearly ordered log this transaction will land. Okay, and then the whole protocol will contain many little instances of this small voting-based protocol. But for the time being, we are going to focus on a single instance with a single sequence number. Okay, let's see what happens. So Vitalik makes a proposal, and when the committee members hear the proposal, they vote. And a vote is basically a signature on the proposal. Okay, now if you are honest, you're going to vote on the transaction you hear from the leader. In this case, it's a golden transaction. So almost everyone is honest in this case because they all voted for golden, except for Loki, right? Loki in this case actually voted for a blue transaction and the red transaction instead. Okay, so this red vote is for a red transaction. Okay, now what do? Step number 3, you wait. You wait until you hear enough votes on the same transaction, and at this moment you can confirm. So when enough people believe that this is the transaction for the sequence number, you are confident enough to say, okay, this must be the transaction. Very simple voting-based protocol. The most important thing to remember about the protocol is that honest nodes vote uniquely. So if I'm honest, I will wait until I hear the first proposal from Vitalik. I'm going to vote on that proposal and only that proposal. I'm not going to vote on anything else. And this uniqueness must hold for every sequence number. Okay, so I want you to keep this in mind because I'm going to give you a very simple consistency proof right now using this property. And to give you the consistency proof, let's first define the parameters we are working with. Suppose there are in total n number of voters, among which less than 1/3 are corrupt. The number of corrupt nodes is bounded. And in this case, I claim we have to wait for 2/3 of the committee to vote. And then it's safe to confirm. And this should give you consistency for the following reason. Imagine Spider-Man has heard 2/3 of the committee voting for the red transaction, and Iron Man has heard 2/3 of the committee voting for the orange. So now I want to prove that these two transactions must be the same. They cannot be different transactions. And how do I prove that? It's very simple. Let's look at the set of red people and the set of orange people. I claim their intersection must contain at least one honest node. And this is because the number of corrupt nodes is less than 1/3. So it's very simple. This is actually just by a pigeonhole principle. We learned it in elementary school. There's nothing fancy here. So now, because this guy in the intersection voted uniquely, we can therefore conclude the red must be equal to the orange. And therefore, everyone should be consistent in what they believe, right? So now let's think about this argument I've just made. If you think about it a little more carefully, the only thing I relied on here is the fact that the honest nodes are voting uniquely, right? I never made use of the fact that the leader must be honest. And in fact, the consistency still holds even when the leader is corrupt. Okay, so with this in mind, let's kind of think about the protocol from these two worlds. On the left-hand side, we have the world when Vitalik is honest. Okay, and when Vitalik is honest, everything's good. We have both consistency and liveness, right? Consistency, I've proven to you. And why do we have liveness? If Vitalik is honest, he is going to propose the same transaction to everyone. And because 2/3 of the committee are honest, right, and they're going to vote, and very quickly, you can gather enough votes on the same transaction, and you can confirm and make progress. So now what happens if Vitalik is corrupt? In this case, we still have consistency because I just reminded you that the consistency argument never depended on the leader being honest. So we still have consistency. Unfortunately, we don't have liveness in this case because if the leader is honest, a leader is corrupt, like one thing he can do is he can just crash. He stops making proposals and no one's going to cast any votes and then the protocol will get stuck. Another thing he can do is he can post different transactions to different people. So now everyone's going to end up voting on a different thing, right? And no transaction will ever gain enough votes. So in this case, you'll get stuck as well. Okay. So it seems like the problem we have to solve is just this little liveness problem, right? If we could solve this little liveness problem, we are all good. So how do we achieve liveness? Unfortunately, this little liveness problem is the most difficult part. And if you look at all these classical consensus protocols, the way they solve this problem is extremely complicated. They have this very complicated recovery path, which I don't want to have to explain. So here's kind of all of these, like most of these classical consensus protocols have this kind of structure. There's a very simple normal path, which consists of one or more rounds of voting, right? Which is like basically the simple voting protocol I talked about. And then when this normal path fails, they resort to a very complicated recovery path to re-elect leader and continue the protocol. Yes, please.
I'm just curious your definition of liveness.
Liveness means you will confirm very quickly in bounded amount of time, and you'll not get stuck, right? So remember, in this voting-based protocol, if the leader is honest, he's going to propose the same thing to everyone, and everyone, like all the honest people, are going to vote based on the leader's proposal. So very soon, you'll collect 2/3 votes from the committee, and then you can confirm. So you make progress, right? Okay. So looking at this picture, one thing we realize is that what we really want is for the system to be operating in the green part almost all the time. Like we don't want this normal path to fail. But then when you look at the code, almost all of the code is actually in this red part. This is like the extremely complicated part of the system, and that's where all the bugs and the complexity are, right? So it's not very desirable. And what's the implication of the complexity in practice? For instance, Chain.com is a company in San Francisco, and they're rolling blockchain solutions for Visa. And they basically completely give up on implementing the recovery path. And all they implemented is this normal path. So now, let's say if the normal path fails, like the leader crashes or something, they have to do all of this manually. And think about 100 banks deploying this protocol, right? And you basically have to go to all these banks. You have to sync their logs manually and then re-bootstrap the protocol. And this is going to be a huge pain in practice. Okay. So now we are kind of stuck at this point, solving this liveness problem. And as I promised, at this moment, I'm going to try to combine the best of both worlds. And the idea is extremely simple. This is classical consensus. I'm going to basically ditch all this messy part and replace it with a very simple blockchain. And this is the fundamental idea behind Cinderella. So I will tell you how to actually instantiate this idea correctly. And here's the terminology I will use. I'm going to call this the fast path and this blockchain the slow chain, right? So you can think of the slow chain as Bitcoin or Ethereum. You can also think of it as a proof of stake slow chain if you don't like proof of work. Okay. And the goal we want to achieve is that we want that almost all the time, the system should be operating in the fast path. And when it's operating in the fast path, we can confirm transactions in 2 to 3 actual network round trips. Okay. And in this fast path, we almost never have to write any messages to the slow chain. Okay, so now even when this fast path fails, it's not the end of the world because we always have the slow chain to fall back to. So in the worst case, we get today's security and performance. Okay, so that's the goal. And just quickly revisit the scenario. Remember, we have a leader, we have a committee. The committee, for instance, can be selected using stake. There's also some algorithm to select the leader. Like both the leader and the committee can rotate over time. But for simplicity, let's consider a single snapshot, right? At this moment, Vitalik is the leader, and these guys are the committee. And there is an underlying blockchain, which we call slow chain. So for now, easiest is to think of the slow chain as Ethereum. Okay. So to get the worst case robustness and security properties of the system, we are going to make a couple assumptions. So we are going to assume the underlying slow chain is secure. And typically this means we need to assume the majority of the miners are honest. If this is proof of work, it means majority of compute power is honest. If this is proof of stake, it means majority of stake is honest. Okay, now we are also going to assume majority honest for the committee. All right. Okay, so here's how the protocol works. I'm going to start from the fast path. I kind of already told you the fast path protocol, but let's revisit it because now I want to highlight what happens when there are multiple sequence numbers. Okay, so remember the leader makes the proposal for every sequence number and then the committee will vote. Okay, now when there are many sequence numbers, in this case we have 1 to 6, I'm going to introduce a notion called notarized. If any transaction gains votes from 3/4 of the committee, it's called notarized. So earlier, remember this number was 2/3 because back then we were assuming 1/3 corrupt. Right now, we want to tolerate minority corrupt. So we have to change the threshold a little bit for that consistency proof to work. Okay, so in this case, we have 1, 2, 3, they have been notarized. 4 is missing the notarization. And then 5 and 6 have been notarized too. In the cryptocurrency system, it's actually important that you process these transactions one by one in a linear order. Because, for instance, 4 and 5 can be spending the same coin. And you must process 4 first before you process 5. Otherwise, there can be double spending. Okay, so now in this case, the only thing we can process is this prefix up to 3. And for the lack of a better term, I'm going to call it the maximal lucky sequence. So the maximal lucky sequence is what you can process and confirm. So remember the problem we are going to solve is the liveness issue when the leader is corrupt. So how do we do that? Well, so far we haven't used the blockchain, the underlying slowchain yet, right? We have got to use the underlying slowchain, and that's where we are going to look for an answer. Okay, we are going to use the slowchain in 2 ways. Number 1, we will use it to collect evidence to detect fast path failure. Okay, and when we detect that the fast path have failed, we initiate what's called the fallback mechanism. And after the fallback, everyone enters slow chain mode and they confirm transactions by posting them to slow chain. But of course, when you are in the slow mode, you can always try to rebootstrap the fast path again. And that's exactly what you want to do in practice because you don't want to be stuck in the slow mode forever. Okay, so I will explain number 1, how to do this detection, and number 2, how to do the fallback. So first, how do we detect fast path failure? And the challenge here is we need a robust mechanism such that corrupt nodes cannot falsely implicate an honest leader. If they can, like they can kind of force the fast path to shut down, and that will be like a denial of service attack. Okay, how do we do this? Here is a quite simple idea. So imagine during normal operation, every now and then, the committee members are going to sign what's called a heartbeat. And this notarized heartbeat, when the heartbeat gains 3/4 signatures, it becomes notarized, right? And then it gets posted to the slow chain. Okay, and what does this heartbeat contain? It contains a cryptographic hash of the current fast path log. So in some sense, the heartbeat acts as a checkpoint. It binds, cryptographically binds to the current fast path log. Okay, normally when things are all good, you'll notice that the heartbeat will keep beating. Okay, and another thing I want to quickly mention is that during normal operations, these transactions on the fast path don't have to be confirmed on the slow chain again, right? The only thing we are posting to the slow chain are the heartbeats themselves, and they're very tiny. Okay, and that's why we can get high throughput because the underlying slow chain has like relatively small throughput, right? So now imagine at some point the heartbeat stops. Let's say for K blocks, I haven't seen any heartbeat. That K is a security parameter, let's say. For Ethereum, you can think of K as 300. Okay, now what do I do? So what can be a reason that the heartbeat has stopped, right? So for instance, if the leader has crashed, stopped making proposals, the heartbeat will stop. Or maybe if like committee members detected that the leader is cheating and censoring transactions, they can complain by stopping signing on the fast path as well. So for all of these reasons, the heartbeat will stop. And this says we must enter the slow chain. We must enter the slow mode. Okay, So that's why I'm going to explain how to do this, how to enter the slow mode through a fallback procedure. Okay, to explain this, I want to also first help us understand the problem we are trying to solve here. So here's the scenario we have. Imagine at some point we all agree through the slow chain that we want to do a fallback. Okay, at this moment, it could be the case that Spider-Man's lock, fastpath lock, ends at 3, but Iron Man's fastpath lock ends at 6. I mean, this is because the network has delay, right? Maybe like Iron Man is receiving notarized transactions faster than Spider-Man. So now the important thing is that these two guys, and in fact, every honest guy must agree on where the fastpath lock ends before they enter the slow chain. Because like once you enter the slow chain, these transactions posted to the slow chain will be appended to this fastpath lock. So in order for you to have consistency, you have to agree. Okay, so how do we solve this problem? If you think about it a little longer, you'll actually realize this is an agreement problem in itself. So in fact, there shouldn't be any simple solution. This is like, we got back to where we started with. All right, but fortunately, we can again use the slow chain, right? And we are going to introduce what's called a grace period, which consists of these K green blocks. Again, K is a security parameter. It can be like 300 for Ethereum. And we are going to use this grace period for people to reach agreement on where the fastpath lock ends before entering the slow chain. So one way to think of it is like, the fast path is an optimistic path. It may fail, but the slow chain is like, it's very slow, but it's sure and steady. It's always there. It's like a public bulletin board I can always rely on. And this public bulletin board doesn't just reside on a single server. It's a decentralized system. So when the fast path fails, people are going to use the slow chain to communicate and reach agreement. Okay, so now how do we do this? Suppose now we all want to fall back. The first thing we do is to stop signing on the fast path. And then we are going to tell each other all the notarized transactions we have seen on the fast path. And now, for every transaction that has been notarized, but it has not been checkpointed yet, I'm going to post it to the slow chain into this green part. So what does it mean, notarized but not checkpointed? Remember, we have the heartbeat mechanism, right? So every heartbeat actually acts as somewhat like a checkpoint, because the heartbeat contains a hash that cryptographically binds to a checkpointed part of the fastpath log. Okay, so for everything that has been vouched for by a heartbeat, you don't have to worry. But if it hasn't been vouched for by a heartbeat, you have to post it to the slow chain. And then by the end of the grace period, we will have completed the agreement process. And one subtlety here is that for consistency, the transactions cannot roll back. Right? Let's say I buy a car from Bar, I pay Bar, I don't know, 1 million Bitcoin. That's a very expensive car, 1 million USD. And then now Bar has received the payment, and she doesn't want the payment to later go away because she has already shipped me the car, right? So it's important that whatever people believe to be confirmed at the beginning of the grace period, this transaction cannot go away after this agreement. But we can prove in our protocol that at the end of the grace period, the maximal lucky sequence contained in the grace period is at least as long as where everyone started with at the beginning of the grace period. So no confirmed transaction will roll back. Okay, so now that's kind of how we solve the Liveness problem. Essentially, we use the heart beating mechanism to detect fast path failure. And once we do detect failure, we initiate a fallback mechanism to enter the slow mode. And again, when we are in the slow mode, we should always try to re-bootstrap the fast path again. Okay, so as I said, to get the worst case security properties, we have to, roughly speaking, assume majority honest. And I want to point out at this moment that we don't have to trust the leader. Even if the leader is arbitrarily malicious and deviates arbitrarily from the protocol, the only thing it can do is to slow down the protocol. A corrupt leader can shut down the fast path and force the system to go into slow mode, but it cannot break consistency and it cannot stop the system either. And that's why fundamentally our system is decentralized, right? It's a very nice trade-off. We have this accelerator that's, it's kind of like a centralized an entity. It's accelerating the protocol, but we don't actually have to trust the accelerator for security or consistency or availability. So fundamentally, we are decentralized. Okay, now, when things are good, we can get instant confirmation. So what do I mean when things are good? If the leader is online and honest, and also 3/4 of the committee are online and honest as well, everything will be very fast because leader proposes, these guys notarize, and boom, everything gets confirmed on the fast path. You don't have to do anything. I mean, almost nothing except for the heartbeats on the slow chain. Okay. So now, to help you remember the protocol, you only have to remember these two sentences. When things are good, we do a single round of voting. Everything gets confirmed on the fast path. When things go bad, we use the slow chain to fall back. Okay. So with these two sentences, you should be able to reconstruct the protocol at home. And of course, I omitted a lot of details today, right? And like I didn't tell you how to do the leader committee election. We have practical optimizations in our system. And in our paper, we have mathematical proofs of correctness. Yes. That's a really excellent question. So what I neglected to mention is that although the accelerator looks like it's logically centralized, in our implementation, it's a distributed system. Like there's a primary and there's multiple geographically distributed backups. And if the primary goes down, we have a very robust mechanism where one of the backups will quickly switch over. So we kind of take care of these like DDoS attacks in the design itself. And that's also why it's very non-trivial to run this accelerator. There's actually quite a bit of, you need a lot of expertise, and also there's quite a bit of operating cost to run the accelerator. So you can think of the accelerator, inaccurately speaking, as like the Akamai for blockchains, right? Like Akamai accelerates the internet. If Akamai is there, internet is faster. If Akamai goes away, internet is still there. It's just a little slower. So we are kind of accelerating blockchains. And Akamai is like a very decentralized system too. Yes, thank you. Maybe you first. And in our V1, we are going to act as the accelerator. But in our V2, we will open up and anyone can launch their own accelerator, maybe their own shard. But we imagine at the end of the day, like it does take quite a bit of operating cost and technical expertise to operate the accelerator. It's not like if you spin up a machine at home, you can be an very fast accelerator. So at the end of the day, we don't think like anyone will be accelerated. There will probably be like a marketplace, maybe, several operators will several accelerators will coexist, but not everyone. Yes, please. Mm-hmm. Okay, sorry, can you repeat the question? The balances, and so mm-hmm. Right, right. So right now, uh-huh. Right. So in our V1, our accelerator is posting these heartbeats to the slow chain. So the accelerator does have to spend Ether to post these heartbeats. In our V2, we actually plan to replace the slow chain with our own proof of stake protocol. So we are using Ethereum to kind of bootstrap. Number one, because that's like, in terms of technical agenda, this will allow us to launch quicker. But also Ethereum already has a very secure and decentralized system, which we can kind of take advantage of for bootstrapping our system. And once we have like a community ourselves, we can replace it with our own proof of stake blockchain. And there's also a bunch of optimizations we can do to make like some primitives native in the slow chain that's kind of targeted for optimizing the fast path. So it will be very nice in V2. Right. So for any decision that you make that requires consistency, so suppose this is Ethereum chain, you have to remove the trailing K blocks for consistency. So K is like 300, and that's like so there are mathematical proofs that show as long as the transaction is buried deep enough in the underlying slow chain, you can get consistency, and the failure probability will drop exponentially fast in terms of the number of blocks you chop off at the end. Mhm. So the nice thing is like we actually don't have to use any smart contracting capability. We are just using Ethereum as a public bulletin board. So there is a smart contract, but we are only posting messages to the smart contract. The smart contract doesn't have to verify any signature because all the Thunder token lives on the fast path, and the Thunder nodes are updating the ledger of Thunder token. Like we are not updating the ledger of Thunder token in the Ethereum contract. Mm. So basically, the committee members will sign the proposal from the accelerator, and then you can aggregate all these signatures into like a more succinct one, and that gets posted. So when this is like a heartbeat, when it becomes notarized, you post this heartbeat and this aggregate signature to the slow chain. But it's just like it's used as a public bulletin board because all the Thunder nodes will read messages from the slow chain, and then they can see, okay, there's a heartbeat. Now there's another heartbeat. Right. The accelerator is posting. Right. The accelerator, if the accelerator is malicious or crashes, we lose fastness. We lose the instant confirmation, and we just fall back to the slow chain. So like this doesn't make it worse. Like we cannot get fastness when the accelerator is corrupt anyway. Mm-hmm. Yes, in the back. Hmm? So for smart contract, we anticipate like, with a single shard, we can do 100 times better than today. But for payments, A to B payments, we can do like maybe 1,000 times better. Like because for EVM right now, like Ethereum's bottleneck is actually the consensus layer. So we remove the consensus layer completely from the bottleneck. The next bottleneck we encounter is like the EVM processing itself. And there with the single shard, if you want to be faster, you have to improve the EVM, like some of the basically this guy all becomes the next bottleneck. We can, yes, that's a very good question. We don't have to use Ethereum. We can use any standard blockchain which allows us to post messages to. The Ethereum is a little easier for us to program because we can just post it to a smart contract. Like we can also use Bitcoin maybe in some clever way, but the transaction fees are also higher on Bitcoin. Yes, please.
Can you talk through two variables? So I guess a governance model around what's happening with these malicious actors in this sort of cycle, and then the second is as we're going from the fast path to the slow path, well, to the fallback mechanism, then the slow path. Um, what's that life cycle look like to go back to that fast path, and what are some use cases that maybe you'll stay on the slow path forever, or maybe you'll just go back to that and
So let's do them one by one. So the first question was like, what do you do with the corrupt actors? So this is like an incentive, like I kind of omitted the incentive part completely, but the reason why people want to behave honestly on the fast path is because they're earning rewards and transaction fees, right? So if the fast path is up alive, everyone earns more and everyone will be happy. So people are actually incentivized to behave honestly. And we can also like introduce some penalty mechanisms, like if you misbehave, you double sign. And then now you can submit evidence to the system to show that I misbehave, and then my collateral can be taken away. So this will incentivize people to behave honestly. And now the second question is about how to rebootstrap the fast path in the slow mode. So this is like, the nice thing is like, you know, in the slow chain, you can imagine there's, in general, you can run like a smart contract to decide what you want to do. Like you can re-elect the leader, re-elect the committee. So there's like, this is more like a also policy kind of a question, right? Yes.
So if I send a transaction to the fast path and the same transaction to the slow path, how do you prevent like overextending?
You don't have to send it to both, because when the system is normally operating, like you only have to send it to the fast path, and it'll just. So what's happening? I kind of omitted this part of the. So you could actually, even when the fast path is operating normally, you could actually post transactions to the slow chain. Let me find a good picture. So even when the system is operating normally, like I can submit transactions to the fast path, but I can submit it again to the slow chain. What's going to happen is like the slow chain is kind of used as a censorship resilient mechanism. So like if the accelerator is dishonest and he's trying to censor your transaction, you can force it to be entered into the lock by posting it onto the slow chain. And then the committee members are going to pick it up. They're going to read it from the slow chain, and they're going to like forcefully insert it into the fast path lock, even if the accelerator doesn't propose it. And now if there are like two transactions, like one from the fast, one from the slow, they conflict, only the first one will take effect. And that's. Hmm? Yeah, all the Thunder nodes are packaged with our own Thunder software, but we also have a packaged Ethereum client right now. So the Thunder node will run an Ethereum node, and all the Thunder nodes will be constantly monitoring the slow chain, like because they have to read the heartbeat messages, and they also have to read these what we call YAL transactions, because like if the accelerator is censoring your transaction, you don't have to worry. There's a way for you to guarantee your transaction to be entered into the fast path just by posting it on the slow chain. So I omitted this part in my talk. Right. All right. Yes.
So in your leader and the voting committee model, so what's the incentive for this node?
So leader and committee get rewards. So they get rewards from participating on the fast path. Like if the fast path is confirming transactions fast, they get more rewards and they get more transaction fees. So that's why they want to participate. But they also have to put down collateral. They have to put stake on the slow chain to be entered into the committee. So the collateral you put down, in some sense, is protecting the fast path. Because if these guys misbehave, like we can take away their collateral, and then they can be penalized accordingly. Yes. That's a very good question. So like I think part of it comes from the incentive. Like the system is actually designed so like in these decentralized systems, it's not good enough to just assume like honest majority. We have to incentivize people to behave honestly. So that's again this reward and transaction fee. This mechanism is designed such that all these people, they are participating in the fast path because they want to earn interest. So of course they are incentivized to participate honestly, and there also can be penalty mechanisms. Like if you double sign, you can lose your collateral. Yeah, I hope this answers your question. Yes, please. So the algorithm I talked about is a single shard. When let's say if your single shard becomes saturated, you may want to have multiple shards. And for smart contracts, like the easiest thing you can do is like these multiple shards act like parallel universes. And now if you want to like read state from another shard, it becomes a little more complicated, and that sometimes is a slower operation. And it's also related to like all these cross-chain techniques. Yeah, so if like the easiest way to think about it is like if I have separate parallel universes, like if these shards don't interact, then it's very easy to do sharding. I can just like spin up multiple of these fast paths and they don't interact. But that's not always the case. Like sometimes you may want to read a smart contract state from another shard, and that requires like some more complicated mechanism to achieve. Yes, yes. challenge process. So how do we like you mean rat out the a malicious accelerator? So in our so for instance, if the accelerator double signs and you can, let's say you see two proposals for the same sequence number, and you can submit these two signatures as like some kind of cryptographic evidence to accuse the accelerator, and then the accelerator's collateral can be paid to the to you. And in our V2, we will open the system up and we can allow multiple accelerators to coexist, and this can create some kind of economy, ecosystem for the accelerators to compete with each other, right? Like if you are not well behaved, you are censoring transactions, you crash often, then like all these users will just move away to a different accelerator and you'll stop making money. And so there's a mechanism, like let's say at a very high level, if I send a transaction to an accelerator and maybe if the accelerator is censoring it, right? So I have a couple of things I can do. One is I can post it to the slowchain to make sure it will guarantee to be entered into the fast path. Or maybe if I'm not happy with the current accelerator, I can move my coin away into a different shard with a different accelerator. So that's like an operation you can do to like, just move your coin into a different shard. So that's something that you can definitely do. Okay. Yes, please. So yeah, these are very good questions. The first question is, sorry, what was the first question again? Huh? How do you select the committee? So right now, we are like selecting up to 500 nodes into the committee, and in precisely speaking, we are selecting people with the largest amount of stake because we want to encourage more stake to enter into this like validation process. The more stake there is, like the more protected your fast path is. But the actual algorithm, like there are some other considerations, so it's not exactly just you take the top 500, right? So the second question is about. Can you repeat the second question again? Yes, that's also a very good question. So right now we are building on top of Ethereum. So Ethereum miners, they're just earning Ethereum rewards. And if you want to be a Thunder validator on Fastpath, you are earning Thunder in terms of like stake mining rewards and transaction fees. So now in V2, we are going to replace Ethereum with our own proof of stake blockchain. So then you can choose to be on the Fastpath or on the slow chain. But it does, you need to set up some kind of a more specialized infrastructure. Like you need to be more well provisioned if you want to be on the fast path. Like any fast path, if you want to run a node, like for instance, you have to spin an extra large node on Amazon EC2 because you have to at least have enough bandwidth to download the fast path log, right? Because the fast path is going to be much faster than the slow chain. If you don't have enough bandwidth, you are going to fall behind. And when you fall behind, the system is designed such that like you start losing your rewards and you'll notice it that you're falling behind the rest of the community. Yeah. So if you are participating on the fast path, and in fact, when we post these heartbeats to the slow chain, the people who have notarized these heartbeats will get rewards. So we use like the slow chain to reach common knowledge about who should be getting rewards on the fast path, and then the rewards are distributed to these people participating on the fast path. Yes, please. And you trust it for fast. Like right now, if accelerator is like our accelerator is like, even if it's arbitrarily malicious, as long as like, let's say majority of the committee are honest, you'll never, you'll never be, be victim of double spending. You don't have to worry about consistency and risk and things like that. Right. Yes. Mhm. It's actually, so that's why we have an explicit staking mechanism. The people who have declared staking recently, they're more likely to be online, and we only need 3/4 of the explicit staking, like the people who are chosen into the committee, and 3/4 of that to be honest and online, and not like 3/4 of the whole stake in the system, because like you may just be a user of the system and you don't care about participating on the fast path. You may not have a node, like extra large node on EC2 to participate. So we want people to, like, if you want to be earning interest, you should explicitly express interest and put down stake on the slow chain to participate. Yes, in the back. That's a very good question. So we are EVM compatible. Anything that runs on Ethereum can directly migrate to our system with almost no change. So it just directly runs on top of Thunder. So Ethereum provides a quite generic programming language. You can use it to implement financial applications, games, like prediction markets. There are lots of examples like dApps that are already running on Ethereum. Like you can go to these websites like DApp Insight and DApp Radar to look at. And right now we have not. We're providing generic EVM support. Yes. Okay, so let me quickly finish. I'm almost done. I've already explained all of the protocol. I just want to kind of talk about some of the deeper insights we gained before we conclude. So, why after 30 years of work, we can suddenly claim to be faster and simpler than everyone else, right? There has to be some deeper insights. So now if you look at all these classical protocols, they work in what's called the asynchronous model. So what is the asynchronous model? It means the protocol is unaware of how long it takes to deliver messages. So in some sense, the protocol is a universal protocol. No matter how long it takes to deliver messages, the same protocol should work. And that's why these protocols are very complicated. Like if you have worked in distributed systems at all, you'll know that asynchrony makes your life much harder. And in some sense, we baited and switched because we are using blockchain, and the blockchain is a synchronous protocol. So what is a synchronous protocol? The synchronous protocol is allowed to know how long it takes to deliver network messages. And for blockchain, like as I said, right, you have to parameterize your block interval based on this delay parameter. Like the block interval, roughly speaking, has to be 60 times the maximum network delay to tolerate like 49% attack. So that's why the blockchain is a synchronous protocol. Now, if you look at all this classical work on distributed systems, including like Google and Facebook's deployment, like people traditionally believe that synchronous systems are slow. Like, because if you think about Google and Facebook, they want like microsecond to millisecond latency. And even waiting for a single block interval or waiting for like a single synchronization round is too much, because the synchronization round, this block interval parameter has to be set very conservatively. If this assumption is violated, then all bets are off. You can lose consistency. Okay. Now, our insight is that this common wisdom is actually not exactly right. And if you look at Thunderella, the interesting thing is, like almost all the time we are operating in asynchronous world. Our fast path is asynchronous. It doesn't have any, like, doesn't have to know network delay parameters. But fundamentally, we are actually a synchronous protocol. We always fall back to the synchronous path. And this is why we can get the best of both worlds. And so now this is putting on my theory hat. Like I want to say this is actually a new theoretical paradigm. And that's why we can claim to be like faster and better than everyone else. For instance, there is a very well-known paper that showed if you want to have an asynchronous consensus protocol, you can tolerate at most 1/3 corruption. This is a very well-known result. It won like the Dijkstra award. Okay. Now, one way to look at this wisdom, this theorem, is like in the classical sense, it kind of says, okay, if you want to be fast, you can only tolerate 1/3 corruption. But now what we are saying is, okay, for Thunderella, we can tolerate up to minority corruption, and we can still be fast almost all the time because we live here almost all the time. So this is like some of these amazing theorems you can get with this new theoretical paradigm. And before I conclude, I wanted to mention that in a large-scale distributed system, simplicity is your best friend. And that's the thing I like the most about Thunderella. Okay, now our company is hiring. If you are interested, you should contact us. And if you are also, DApp developers who want to build the next generation, like the more sexy, much attractive Thunder Kiddies, you should also contact us. We are going to be having a hackathon at the end of June, and this has the information. So, come and check it out. Okay, all right. Yeah, we have all sorts of positions, including like, developer and community management, marketing, interns, research. So just contact us. And our company is in Sunnyvale downtown, and you can come by and visit us. Thanks.
We're not confirmed in participating yet, but the people who are hosting a hackathon are actually also here with Dora hats. And I know it will be really cool. So yeah, encourage everyone to try it out.
Okay, and thank you for the excellent questions.